Hi everyone, welcome to the course on measurement and instrumentation, and this is our fifth lecture of our sixth week of discussion, and we are talking about analog meters, and today we will continue our discussion on energy meters. If the time permit, we will also talk about different AC bridges which can be used for the measurement of inductance, capacitance, phase and frequencies. Okay. So, we were discussing the energy meters and we discussed that energy is the total power delivered or consumed over a time interval, or we have defined that energy is equal to power into time. Okay. And in more specific way, if you know the voltage and current, okay, like if there is a meter which has to measure the energy, okay, it should be fed with the voltage and current in volt and ampere, okay, and it will try to integrate it over certain time period, okay, to calculate the energy. Okay. So, energy can be given, we know that, as integral over 0 to t v into I into dt. Okay. And the unit of energy is joule or watt second, which is say 1 watt over say an interval of 1 second or similar time units. Okay. We have also talked about per hour and so on. Okay. Now, let us discuss about AC and induction type energy meters, which is very popular and is the one which is used in our household for measurement of energy that we consume, or the meter that is installed in our houses. Okay. So, AC induction energy meters are designed to operate only with the AC currents, okay, and are commonly used for measuring electrical energy in AC systems. Okay. Based on the nature of supply, these meters are classified into two types. We have single phase induction meter, which is the one that I was talking about, and then we have the industrial grade induction meters, based energy meters like three phase induction meters. Okay, and which is usually part of industrial instrumentation courses. Okay. In this course, we will mostly focus on single phase induction meter. So, induction type energy meters are extensively employed for the measurement of electrical energy consumption in single phase, in mostly in domestic as well as in certain industries. Okay. These meters operate on the principle of electromagnetic induction, like any induction meter that we have discussed in our module earlier. Okay. And that is why they are inherently suitable for AC system, because here you are not dealing with magnets, basically you are dealing with electromagnets and all. Okay. In general, if I talk about its construction, the construction of induction type meters are done in such a way that it ensures that there is low or minimal mechanical friction. This is because they use a lightweight rotating aluminum discs and precision bearings. Okay. So, these lightweight aluminum discs are used to ensure that this aluminum disc is rotated when there is a change in voltage, or when there is a flow of current, okay, or when there are both. Okay. And its rotation is actually mapped to the number of time it has rotated. Okay. And accordingly it tries to integrate the power over energy. So, when power rises, its rotation also increases. Okay. So, this single phase induction meters are preferred because they exhibit high torque to weight ratio. This enables reliable operation even at low load conditions or low load currents. Okay. Induction energy meters are very economical to manufacture, because as I have mentioned, there are two electromagnets and aluminum drive rotated. Of course, there are multiple components that we will discuss while we will talk about its construction in little detail, but in general this is a low cost analog tool. Okay. And they are, of course, they are very much acceptable across households as well as certain industries. Okay. These tools offer good measurement accuracy and maintain consistent performance over a broad range of load, okay, and the load variations. Okay. These meters demonstrate stable characteristics under varying temperature conditions, although there are certain issues with temperature that we may talk about later, but mostly under varying temperature conditions also their performance are intact. Okay, this temperature less dependency on the temperature ensures their long term reliability, and they are also kind of not that frequent in calibration. Okay. So, in all induction type instrument, two magnetic fluxes are generated by current flowing through a separate winding of the instrument. Okay. So, you have two fluxes like any other induction type instrument. Okay. And these magnetic fluxes are alternating in nature and are displaced in time in phase also with respect to each other. We will take one example of two fluxes, and then we will see that how mathematically it results in certain force which rotates the disc. Okay. So, the alternating fluxes that we were talking about actually intersect a conducting metallic element, and the metallic element that we have already talked is the aluminum disc, okay, or sometime drum, but mostly the disc, okay, which usually act as a moving system of the instrument. Okay. And due to the time varying magnetic flux, electromotive forces EMFs are induced in the metallic disc. Okay. And in accordance with the Faraday's law of electromagnetic induction. Okay. So, we know that E is equal to minus d phi by dt from Faraday's law, and accordingly you have a induced EMF in the disc because of both the fluxes. Okay. Now, the induced EMF gives rise to eddy currents circulating within the conducting disc. Okay. And the interaction between the eddy currents and the alternating magnetic fluxes produce a electromagnetic torques. Okay. So, we have two different fluxes, means that there will be two different eddy currents. Okay. And there is a high chance that eddy current of one may interact with the flux of second, okay, or flux of the second coil, okay, or you can say simply the second flux and vice versa. The first, or you can simply say that the second eddy current interacts with the first flux or the flux generated by the first coil. Okay. So, this is basically important for the operation of the induction type instrument, and we will see it exactly that how these fluxes are generated and how they interact with the eddy currents generated by these coils. Okay. Now, this is a simple figure which shows a thin circular aluminum disc free to rotate about an axis through its center. So, this is the center across which it is rotating. Okay. Now, there are two poles P1 and P2, as you can see, okay, P1 and P2, okay, which is producing alternating fluxes phi 1 and phi 2, and these fluxes are cutting the disc, as you can see. Okay. Now, any annular portion of the disc with center on the axis P1 will be linked by alternating flux phi 1, and hence it will have a induced EMF that we have just seen as per the Faraday's law. Okay. Now, this induced EMF will produce a eddy current I1. Okay. Now, similarly, because of the pole 2 that we have seen, a flux phi 2 is generated, and this produces a eddy current, say I2. Okay. Now, the presence of two alternating magnetic fluxes result in the generation of two corresponding eddy currents that we have just seen. Okay. Now, consequently, two electromagnetic torque components are also produced. So, torque due to the interaction of the first magnetic flux with the eddy current induced by the second magnetic flux, and torque due to the interaction of the second magnetic flux with the eddy current induced by the first flux, or you can simply say the torque due to interaction of the first magnetic flux, okay, or phi 1, okay, with the eddy current induced by the second flux, which was I2, if you remember. Okay. So, we have torque, say I am calling it TD1, okay, and this as TD2. So, I have torque TD1 due to the interaction of the first magnetic flux phi 1 with the eddy current induced by the second flux, which was I2. So, because of the interaction between phi 1 and I2, there is a torque, and then similarly there is another torque because of the interaction of phi 2 and I1. All right. Now we have two different torques acting in different direction. So the net operating torque of the induction instrument is the algebraic sum of these two torque components. Okay, so which this actually torque drives the motion of the moving system. All right, so we can see whatever we have discussed right now in better way if we visualize it through some mathematical equation. Okay, so for that we have initially two components, the two fluxes. So let phi 1 and phi 2 be the instantaneous value of two fluxes having a phase difference of certain value, say beta. Okay, and therefore two fluxes can be written in a way so that they have a phase difference of beta. Okay, so if I say that phi 1 is equal to a constant, say another phi m1 and into sine omega t, then phi 2 can be phi m2, okay, into sine omega t, which is displaced by a phase difference of say beta. So from first equation I have phi 1 equal to phi m1 sine omega t, and phi 2 is phi m2 sine omega t minus beta. Of course, this phi m is the peak value that I am talking about for the flux. Okay, so if I want to calculate the RMS values for these fluxes, they can be given by these two equation 3 and 4. Phi 1 can be given as phi m1 divided by root 2, while phi 2 can be given as phi m2 divided by root 2. Okay, so I have two different fluxes, phi 1 and phi 2, okay, which can be written as phi m1 sine omega t and phi m2 sine omega t minus beta, okay, and their RMS values can be given by these two values that we have just seen in equation 3 and 4. Okay. Now flux phi 1 produces an EMF in the disc by a transformer action. Okay, transformer action we know is the EMF generated. The equations can be given something like this. So the instantaneous value of this EMF can be given as E1, which is directly proportional to minus d phi 1 by dt. Okay. Now from equation 1 we have already seen that phi 1 is equal to phi m1 sine omega t. So we can simply write equation 5 as in terms of this phi 1 as phi m1 sine omega t, and E1 can be given as E1 is directly proportional to minus d by dt phi m1 sine omega t. All right, I am calling this equation as equation 6. Okay. Now if you simply take the derivative and all, you have E1 directly proportional to minus phi m1 omega sine omega t, and since this omega is equal to 2 pi f, okay, I can simply replace this omega with f, because we are not taking this any constant right now, because I am talking mostly in terms of this proportional constant or proportionality values. Okay, so I am just now ignoring the absolute values, and E1 can be given as E1 directly proportional to minus phi m1 into f into cos omega t. I am calling this proportionality as equation number 9. Okay. Now it is clear from this value that E1 lags the flux phi 1 by an angle of say 90 degree. All right. This is exactly what we see in the transformer action. Okay. Now consider that capital E1 is the RMS value of EMF E1, the small E1 that we have just talked about. Okay. E1 can be given as phi m1 into f by root 2. Okay. Or E1 can be directly given proportional to phi 1 into f1, or E1 is basically phi 1 into f1. I am calling this equation 11. All right. Now this EMF circulates an eddy current having a RMS value of say I1. Okay, and if the impedance of the eddy current path is Z, okay, I1 can be given as again in the terms of proportionality as E1 by Z, this impedance of the eddy current path. All right. So, but from equation 11 we have seen that this E1 is directly proportional to phi 1 into f. Okay. Now I can simply replace this E1 by this value from equation 11, and I1 can be given as phi 1 into f by Z. Okay, and this equation is very, very important. Okay, the eddy current having RMS value I1, this I1 is directly proportional to phi 1 f by Z. All right. Now I1 lags the voltage E1 by certain angle, say by angle alpha, which will be obvious. okay, because we have seen that this E1 was lagging by phi, and therefore this I1, which is induced by because of the flux, will be again lagging behind this E1, okay, and say it is not 90, it is certain angle alpha, okay. Now this alpha, if we talk about tan alpha, okay, tan alpha will be the ratio of the reactance to the resistance of path of the eddy current in the disc, okay. So if I talk about tan alpha, alpha is the angle or the lag that is I1 having between, or say phase angle between I1 and E1, all right. So tan alpha can be written as reactance of eddy current path, all right, that we have just now seen, okay, divided by actual resistance, all right. Now a phasor diagram can be drawn for all these parameters phi 1, phi 2, I1, I2, E1, E2, and a phasor diagram looks something like this, okay. So if you see this phasor diagram, the phase angle between phi 2 and I1 is equal to 90 minus beta plus alpha, all right. So simply say if this is 90, okay, which was the phase angle between phi 1 and E1, so this angle can be given as 90 minus beta, all right, and then you are calculating the phase difference between phi 2 and I1, so this angle plus this angle, okay. So this was 90 minus beta and this is alpha. So the phase angle between phi 2 and I1 is 90 minus beta plus alpha. Similarly, you can calculate the other phase differences, okay. Now we have seen that we have two different torques, TD1 and TD2 earlier, okay, and the average deflection torque TD1 can be given as deflection torque produced due to the interaction of flux phi 2 and current I1. This current I1 is produced, the eddy current I am talking about is produced due to flux phi 1, okay. So TD1 is the average deflection when there is a interaction of flux phi 2 and current I1, okay. So TD1 can be given as TD1 proportional to phi 2 into I1 into cos 90 minus beta plus alpha, all right. However, we have seen from equation 12 that I1 is directly proportional to phi 1 f by z, okay. And if we replace this I1 in equation 14 with this value of I1 from equation 12, we get TD1, the torque, the average torque, okay, equal to phi 2 into phi 1, okay, phi 2 into phi 1 into f by z cos 90 minus beta plus alpha, and I am calling this equation 15. So we have written equation for flux phi 1, okay. Similarly, we can also write for phi 2, okay, similar equation can be written, okay. And again, if I refer to the phase diagram as we have seen earlier, okay, the phase angle between phi 1 and I2 can be calculated. So this is phi 1 and this is the I2, all right. So this can be calculated, okay. So if we calculate this, this will be coming to be 90 plus beta, okay, plus alpha, all right. So this will be the phase angle between the flux phi 1 and the current I2, similar to what we have seen earlier. It was 90 minus beta plus alpha, okay. Now we have also seen previously the torque equations TD1 and TD2, okay. So average deflection torque TD2 in this case will be equal to the deflection torque produced due to the interaction of flux phi 1 and current I2, where the I2 is the RMS value of the eddy current which is induced due to flux phi 2, okay. So TD2 can be given as phi 1 into I2 into cos 90 plus beta plus alpha, okay. However, we have seen earlier that I2 is directly proportional to phi 2 into f by z, okay, and if I replace this I2 with this value, TD2 can be given as phi 2 into phi 1, okay, f by z cos 90 plus beta plus alpha. All right. So, this is the second torque that we are talking about. Okay. We will come back to this torque again. Okay. Now, consider that the positive direction of the magnetic fluxes be defined as indicated in this figure. Okay. Now, assume that at the instant under consideration, both magnetic fluxes are increasing with time. Okay. Now, according to the Lenz's law, the induced electromotive force EMF will oppose the change in the magnetic flux which is producing them. Okay. Now, as a result, the direction of the induced eddy current I1 and the current I2 in the conducting disc are established such that they oppose the respective increase in the fluxes. Okay. And this is very important for the movement of the disc. Okay. So, the direction of current I1 and I2 are as shown in the figure that you can see. Okay. And this is consistent with the law of the electromagnetic induction. All right. So, if we apply the left hand rule, we find that the flux phi 2 interacting with current I1 produces a force F1 which is acting from right to left. Okay. And similarly, flux phi 1 interacting with the current I2 produces a force F2 which is acting from left to right. Okay. So, now you have two forces because of the interaction of the flux phi 2 with current I1 and flux phi 1 with interaction with I2. Okay. So, two forces are there, they are in opposite direction. It means that you have two different torques. Okay. TD1 and TD2 again acting in the different directions. Okay. So, if I have to calculate the total deflecting torque TD, mathematically it can be simply given as TD equal to TD1 minus TD2. Okay. Where TD1 is produced by interaction of phi 2 I1 and TD2 is produced by interaction of flux phi 1 and I2. Okay. So, TD is directly proportional to phi 1 phi 2 f by z. Okay. And you have cos 90 minus beta plus alpha minus cos 90 plus beta plus alpha. Okay. And if you solve this, of course, I am not considering the mathematical constants, but if you solve this TD, the deflecting torque comes out to be phi 1 into phi 2 into f by z into cos alpha into sin beta. Okay. And this equation is very, very important, and this is the actual deflection torque which is acting on the aluminum disc that we have seen. Okay. So, the electromagnetic torques developed is directly proportional to cos alpha, that we can simply see from this equation. This TD is directly proportional to cos alpha. Okay. So, means that to obtain a maximum torque, the angle alpha should be as close to 0, so that cos alpha is maximum as possible. Okay. Now, this condition is achieved when the eddy currents is nearly in phase with the inducing EMF. Okay. So, therefore, the path of the eddy currents should have highly electrical resistance which minimizes the phase lag of the eddy current. Okay. It should be as resistive as possible. Okay. So, a larger effective torque is produced, improving the sensitivity and performance of the induction instrument if you have the highly resistive path. All right. Now, we can also see from this torque equation that it is proportional to electromagnetic torque which is developed TD is directly proportional to sin beta also along with the cos alpha. Okay. So, it means that to obtain maximum torque, the angle beta should be as close to 90 as possible, so that the sin beta term is as high as possible. Okay. So, the angle beta represents the phase displacement between two magnetic fluxes. Hence, for efficient operation, the two alternating fluxes must be phase shifted by nearly 90 degree. It should be very near to 90 or it should be 90. All right. So, maximum torque is achieved when beta is 90 degree. Okay. So, when two fluxes are in quadrature, this will result in optimal interaction between fluxes as well as the eddy currents. Okay. So, this is fundamental of how this measurement, the energy meters work. Okay, but we have mostly seen the deflection, but it is not only the part of energy meter. Along with the deflection system, you have other parts also. So if we see the construction of a generic single phase induction meter, it looks something like this. Okay, so if you see, you have four main components of this energy meter. Okay, you have a driving system, you have a moving system, a braking system, and a registering system to count the number of rotations. Okay, so four different components or four different systems, when they come together, they make this energy meters. Okay, so if we see the driving system of the meter consists of two electromagnets. Okay, the core of these electromagnets is made up of silicon steel lamination. Okay, now coil of these two electromagnets are called current coil, sometimes also known as series coil, because they are connected in series with the load so that it carries maximum load current. And then we have pressure coil, which is also known as shunt current, which is connected across the supply voltage, so it carries current according to the voltage. Means that if you remember our first equation that we have discussed today, the energy meter will require the instantaneous value of voltage and current so that it can multiply it. Of course, you have to integrate it over certain time period, right? So you have both these coils present to feed the current, maximum current and maximum voltage. Okay, the driving system of this single phase induction motors also has a very important component, which is known as copper shading bands, and these copper shading bands are used in such a way that they are able to adjust the copper rings on the core. So their main job is to shift the pressure coil flux by 90 degree or make it in quadrature with the supply voltage for correct working. So it acts as a kind of phase corrector for the energy meters. Okay, then we have a driving system. So this driving system that we are discussing, okay, they are actually known as driving system because it produces a driving torque which rotates the aluminum disc. Okay, now torque is created by the interaction of the fluxes that we have just seen between the current coil and the pressure coils. Okay, and now along with the driving system, we have a moving system which consists of aluminum disc which is mounted on a light alloy shaft. Okay, which is placed between series and shunt magnets. Okay, the shaft rotates on a pivot, okay, or the jewel bearing. Okay, and a special gear is there to connect it with the counting mechanism or the registry mechanism. Okay, then we have braking system. Braking system is nothing but a permanent magnet. So a permanent magnet which is placed near the edge of the aluminum disc acts as a braking system. Okay, so when the disc rotates in the magnetic field, it produces a braking torque, and this torque can be adjusted by shifting the permanent magnet's position and the disc position. Okay, then we have registering mechanism or counting mechanism that we have just seen. Okay, the registering mechanism is used to continuously record the energy consumed. Okay, and it shows a reading proportional to the number of revolutions made by the rotating disc, because this is the way by which you are actually integrating the power or the multiplication of voltage and current over certain period of time. Okay, so if I summarize whatever we have discussed, okay, the induction type energy meters, you can say that they are economical, and they are not only economical, they are also rugged kind of device. Okay, you have electromagnets, you have aluminum disc, you have the permanent magnet for braking system and all. Okay, so overall the construction is very simple and they are cost effective. Okay, and that's why they are very popular. However, they also suffers from mechanical wear because a disc is rotating. Okay, they are frequency dependent and they have a poor accuracy under low load and distorted waveform. Okay, fine. So this is how the energy is measured. Okay, we can again measure phase, frequency, which is inductance, capacitance, all these things using different bridges, particularly the AC bridges. Okay, so AC bridge is one of our important thing that we wanted to discuss. However, because of the time constraint, what we will do is we will talk in generic in a general way what is the AC bridge. okay, and then we'll see that how it can be extended to measurement of all these components. Of course, if the time permits later on, we will again come back to this and we'll try to see that how with some example that how it can be used for measurement of different parameters, okay. However, mostly this, if you understand the Wheatstone bridge concept, it is not that difficult to understand this concept of AC bridges, okay. So, AC bridges are used for the measurement of inductance, capacitance as well as other parameters that I have mentioned, while DC bridges are used for measurement mostly of the resistance, and you can say that these AC bridges are the extension of Wheatstone bridges, okay. So, the bridge circuits are null type instrument, means that the measurement is taken when the detector shows zero deflection, indicating that the bridge is in the balanced condition, okay. So, in general way, the AC bridge, as you can see in a balanced condition, if say this is the impedance 1, say this is 2, this is 3 and 4, okay. You can say that the AC bridge is in balanced condition when the impedance of branch AB and say CD, okay. So, Z1 theta 1, Z2 theta 4 is equal to multiplication of Z2 theta 2 and Z3 theta 3, okay. Or if I simplify, Z1 Z4 and the phase is theta 1 plus theta 4, okay, and Z2 Z3 and the angle is theta 2 plus theta 3, okay. So, if you take the mod, the impedance part of this impedance, okay, the mod of Z1 into mod of Z4 is equal to mod of Z2 and mod of Z3, okay. This condition is in the balance condition, okay, and the angle theta 1 plus theta 4 is equal to theta 2 plus theta 3, okay. This is two generic condition for these AC bridges to be in the balanced state, okay. Now, in DC bridges, we have a very nice galvanometer which is used as a detector to indicate the balance condition. You have zero current flowing in the galvanometer and you say that the bridge is balanced. However, in AC bridge circuits, different type of detectors are used depending on the frequency of the AC source, okay. The one important thing that is there in the AC bridges is that is the quality factor, okay. So, quality factor is defined as by this equation. Quality factor is equal to 2 pi into maximum energy stored by energy dissipated per cycle, okay. So, a high Q value indicates that the circuit stores more energy and loses very little energy during each cycle, because this numerator term is high in this case, okay. Now, the dissipation factor D is nothing but the reciprocal of the quality factor. So, D is equal to 1 by Q, okay, and represents the ratio of energy dissipated to energy stored, alright, just reverse of this, okay. Or in generic way, in the power term, you can say that this quality factor is equal to 10 phi, which is equal to reactive power by real power, where phi is the power factor, okay. So, for a series configuration of inductor and a resistor, the quality factor is given as omega L by R, while for a parallel connection it is equal to R by omega L, okay. Similarly, for a series combination of resistor and capacitor, quality factor is given as 1 by omega C R, while for their parallel connection, quality factor is given as omega R C, alright. So, low frequency ranging from about 2 hertz to 200 hertz, you use a vibration galvanometer. Then for different range, like for 200 hertz to 2 kilohertz, you use something else, okay. For higher frequency above 2 kilohertz, again you use another way to measure this, like tuned amplifier detectors, okay, because of their accuracy and all, okay. Now, the measurement of inductance can be carried out using different type of AC bridges, okay. And what type of AC bridge we will use will depend on the quality factor of the inductor that is under measurement, okay. So, you have a Maxwell's induction bridge, okay. Then you have Maxwell's LC bridge, okay. You have Hayes bridge, Anderson's bridge and all, okay. So, this again depend on the quality factor of the inductor. So, if the quality factor is less than 1, usually the Anderson's bridge is preferred, okay. And if it is greater than 10, the Hayes bridge is something that we utilize to measure inductor, okay. Similarly, for frequency and other parameters which is related to AC parameter, you have other kind of bridges like Wien's bridge and other bridges that you can use, okay. Similarly, for capacitance, you have two different ways. You have de Sauty's bridge and the sharing bridge. Okay, usually de Sauty's bridge is very popular, and let's see one example so that you can extend the knowledge to other bridge configuration also for the measurement of other AC parameters. Okay, like this is one of the configuration for the de Sauty's bridge. Okay, now if I have to find certain unknown value, in this case, say I have unknown value of C1, for example, I want to measure this. Okay, so I have in this configuration, we have already seen that when a bridge is balanced, means the multiplication of Z1, Z4 is equal to Z2 into Z3. Okay, now if we see this, this is branch 1, this is branch 2, this is branch 3, and this is the branch 4. All right, so if I see the impedance of branch 1, okay, it is say R1 plus 1 by j omega C1. Okay, now R1 plus 1 by j omega C1 multiplied by the R4 value. Now this value is equal to 1 by j omega C2 plus R2, and then this multiplied by another resistive factor, that is R3. Okay, now if you simplify it and you take this R4 to the other side, okay, you get R1 plus 1 by j omega C1 equal to R2 R3 by R4 plus R3 by j omega R4 into C2. Okay, now if I compare the resistive part and the real part and the imaginary part, if you compare it, okay, for the balance condition, R1 is equal to R3 into R2 by R4, while if you compare 1 by j omega C1 is equal to R3 by j omega R4 C2. Okay, or simply I can say that C1 is equal to C2 R4 by R3. Since all these parameters are known, C2 was variable to bring it to the balance condition. Okay, R1 can be given as, if you know the values of R3, R2 and R4, since R2 and C2 were varying. Okay, if you know the R3, R4 and R2 values, R1 can be simply calculated as R3, R2 by R4, while C1 can be calculated as C2 into R4 by R3. Okay, so in this condition, the de Sauty's bridge help you in finding the capacitance value as well as the impedance value of this unknown impedance of branch 1. Okay, so this is just one way of measurement of capacitance. Similarly, you can see that other bridges that we have just talked about, depending on the Q factor, you can extend it for the measurement of inductance. Okay, and similarly you can use it for the measurement of frequencies, phase and other parameters. Okay, so in the interest of time, we have to stop here. Okay, and we will start from the next week new module. So 7th week will be dedicated to our third module, which is transducers. Okay, and in the initial lectures of transducers, maybe in the complete 7th week, we will focus on two different physical quantities measurement, that is temperature and pressure. Subsequently, we will move to other week where we will talk about some more transduction techniques. Thank you.